let me start the recording. Awesome. Welcome, friends. This is yet another adventure with Deep Learning Adventures. If you're joining us from Meetup, you can find us under Deep Learning Adventures. If you're joining us from YouTube, if you search for Deep Learning Adventures on YouTube, we have several playlists where we have gone through different interesting challenges, all the way from TensorFlow to coding challenges, and recently we're diving into Kaggle and specifically what are called mini courses. And as you can see here from this playlist, we've tackled Python, intro to machine learning, data visualization, a little bit more advanced machine learning, pandas, an introduction to deep learning, some feature engineering. And last Wednesday, Liana covered for us an introduction to SQL, which was really good hands-on coding session. I highly encourage you to check it out. Today we'll wrap up SQL. We'll do a more advanced session on SQL. That will take our SQL skills a little bit to the next level and hopefully help us answer some more interesting challenges, be it on your business data, on your project data, whatever it is. So again, this is a mini course called Advanced SQL under Kaggle. And again, if you go under kaggle.com/learn, you're going to see all the different ones. And we've tackled some of them in the past, and we have a few more left to finish, hopefully this year. Cool. So today we're going to talk a little bit about join and unions, some analytic functions, some nested and repeated data, as well as writing efficient queries in terms of storage, as well as time execution. So should be interesting. And again, if you have questions or feedback, feel free to chat or feel free to unmute yourself when I ask you for questions. Awesome. Let's start right away with joins and unions. So let me zoom in a little bit so everybody can see. So last time we saw a very simple example of a join operation between two tables. If you remember, we had an owners table and a pets table, and each one of them had a unique identifier for the owner as well as unique identifier for the pets. Let me find this new Paint program that I was able to download. Yep, Screenbrush. Perfect. Okay, I like this program. It's called Screenbrush. Yeah. So yeah, so we look at the owners table, we look at the pets, the pets table. It's kind of hard with the mouse pad. And we saw that we wanted to join these two tables, and they needed to have something in common. And in the SQL world, that was called a foreign key. So the pet ID column here, what is what is called a foreign key that is used to be joined with the pets table on the ID field here. So that means that owner Audrey has pet ID, or is related to pet ID 1, and pet ID 1 actually corresponds to this pet, this rabbit right here, Dr. Harris, and so forth. Today in this table, we see some new entries. We see that Veronica does not have a pet, and we have a pet here with pet ID 5 that we don't see anywhere in this table. That means that this dog does not have an owner. Cool, so keeping that in mind, let's see what kind of join operations we can do. Why is mine letting me scroll? Right, quit. Cool. So we saw last time we did a join, which is basically an inner join between the two tables, and that will only give us as results pets that have owners and owners that have pets. So in this case, Veronica and Mace would not be returned in our example simply because they don't exist on both tables. So we're doing what is called an inner join. Our data has to exist on both tables, both the owners table as well as the pets table. There are different types of joins. We can do, so we saw an inner join where we only get results that are common in both tables. We can do something called a left join, and left is relative to the first table that is mentioned in our join statement. So for example, here we have owners is the left table, left join with pets. That means that we're going to retrieve all the owners regardless if they have a pet or not. If we wanted to look at all the pets regardless if they have an owner or not, we would have done a right join. And if we wanted all the pets and all the owners, meaning a few more people, then we would do a full join. So in this case, you see the owner doesn't have a pet, Veronica, and Maze doesn't have an owner. Cool. So that was us concatenating data on what is called horizontally. We basically expanded our tables horizontally. What if we want to expand our data vertically? So what if we want to basically combine different data of the same data type under one contiguous column? So let's say maybe we're interested in all the owners, or maybe all the ages, or something else that is common in both tables. Then in that case, we would do what is called a union operation. So in this case, what we're doing here is we're looking at all the age field from the pets table, as well as the age field from the owners table. They don't have to have the same name, but they should have the same data type. So they should either be the same, number, characters, floats, you name it. And in this case, we're doing what is called a union all, and that will simply combine all the ages for each record in the pets table with all the ages in the owners table. And you see here that 9, for example, is repeated twice, and that's because we're doing a union all. So we're basically keeping duplicates. There's no deduplication happening here. If we wanted to include only unique values for a field, we would do something called union distinct. That means that in this case, for example, in this entry 9 here would only appear once. We're going to look at some more examples from a real data set.
George, on those unions, so you said the selecting age, it doesn't matter that it's the same name. If it's two different names, do we want to name them to the same thing using an as, or will it just appear as two different columns if we don't do that?
That's a good point. I haven't tried that. I would imagine maybe as would be the right approach. I don't know, or I don't think it will return two columns. I haven't tried it. That's a good one. Maybe you can try it on one of the exercises. Unless you know the answer. I don't know.
No, I don't.
Yeah, we can try it. I'm curious too now.
Hey, George, this is Ted. Same column name's not required.
Yeah.
They're just columns are aligned in order.
Right. So it could be ages, could be something else. Yeah. You just end up with one column.
But I think they have to have the same type.
Yes, that's important. Yeah, you need the same type. Otherwise, this wouldn't work. Yeah, names can be different, but data types must be the same. All right, let's look at a real life example. This is from this Bigquery data set on Kaggle on Hacker News, and we saw it a little bit last time on comments and posts, and it was an interesting data set. So let's see what data, let's refresh our minds a little bit, and let's see what operations we can do. So again, if you remember from last time, this is us connecting to Bigquery. Bigquery is just the infrastructure that allows us to pull large amounts of data. We typically don't need it for your projects, but let's say if a data set is hosted on Bigquery, it's very easy for us to connect to it and do all kinds of SQL operations. So we're mainly using this for infrastructure hosting. So in this case, we'll connect to this project called Public Data and has a lot of data sets under it. One of the data sets is called Hacker News. And a data set is basically a collection of tables. And we're specifically looking at the comments table. So once we pull that in, we're looking at the first 5 records of that table, and we're converting that actually to a data frame, and here is the content of it. So we have an ID, by, author, time, timestamp, text of the comment, the parent, which is, if you remember, the ID of the original post, and some other fields. So this is one table that we're looking at, comments. Another one is stories. And this is the original story that was written, and those are the comments belonging to different stories. So we're pulling that table as well, stories. We're just looking at the first few rows, and we have an ID, a story ID, a by, which is the author, a score metric, timestamp, the title, the URL, the text, and another field for the author. So what we're going to do here is we're going to look at both tables, stories and comments, and we're going to, just for the sake of keeping it simple, we will only look at January 1st, 2012. We'll only look at a very specific day, and we'll look at all the stories as well as all the how many comments did each story in January 1st, 2012 had. Maybe we can sort them by popularity in terms of comments. Okay, so in this case, we're going to use what is called a comment table expression. We saw that last time, and that's very handy because it allows us to basically do operations before, or narrow down our search before we join it with other data sets. So it helps us both in terms of data as well as execution time. So in this case, we start with the from statement. So we're looking at the comments table. We're looking at the parent field, which points to the story that a comment belongs to. We are counting how many comments does each parent record have. So basically, how many comments are under a story. And we're going to call this whole result, or this whole intermediate table, SC for comments. Then later on, we're going to join it with the stories right here table. We will do a left join on C. We're interested in we are interested in all. Sorry, we're doing a stories left join with C. We're interested in all the stories, regardless if they had a comment or not. That's why we're doing a left join. And the thing that is common between them is the story ID is equal to this comments parent ID that we saw above. And then we just need the story ID, give it a nice name. By is the author, title is the story title, a number of comments is coming from here, and the expression. We want to filter down this search a little bit. That's why we're doing this extract date from this timestamp. We don't really need the times portion of the date, so we're doing a date, extract date, and we're just interested in January 1st, 2012. And then we will want to sort all these results by number of comments, descending. So run the query, we convert the result to a data frame, we just look at a few records. And again, the order should be story ID, by, title, and number of comments in descending order. If we look at the very end, there are probably going to be some stories that don't have comments. Yep, so we're looking at the very end here. These are the stories that don't have any comments, and they appear because we did a left join on stories and comments tables. Cool. Let's look at a union example. Let's say we wanted all the usernames of users who wrote stories or comments. So this is the key here, stories or comments on January 1st. So this is just a filter on the overall result. But here we have to keep in mind there are two tables, stories and comments. And we need all usernames, and we don't want duplicates. So that means that we're going to use this union distinct instead of union all that we saw above. So let's start from the from statement. We need a comments table. SC, we filter it just for that date. So basically we're just getting the author ID here, the by field. Then we're unioning it with the stories table. And again, we're filtering for the same date. And now both the author of the comment as well as the author of the stories are character fields, and we're just doing a union distinct to see unique users. And if we look at the first few records, those are some sample record or user IDs. Cool. So let's see if we wanted to get the number of users who posted on January 1st. So these are users who posted on January 1st. Let's look at it. That's about, and this is the length of the data frame. And we don't have to do anything else. It's just about 2,000 users. And that's it in terms of union and joins. We have an exercise, but I'm curious if you have any questions so far. Let me go back to this diagram here. Something that helps me, and we're going to see that later on, but something that helps me is what is called this order of operations in SQL. And that's something that we're going to revisit, especially in the very end where we talk about writing efficient queries. So the way that these SQL statements are executed are in this specific order. So first of all, we start with a from statement. We look at the tables, we do any joins to just basically get the underlying data set. So if your join is complex, this is where you might focus to make it more efficient. Once we get the entire data set from this join or distinct or union, then we filter down the data by using the where statement. So we saw about we filter only for a specific day. After that, let's say we want to group by specific users or specific user ID, or maybe by title. You can do what is called aggregations. We do that by the group by statement. You can filter also in the group by statement using the statement having. That's also used as a filter for aggregated data. And at the very end, then we finally select what we need, what fields we need from this order of operations. There's an optional as well, order by, where we can sort the data. That doesn't impact the amount of data, it's just the order they appear to the user. And if we just want to limit maybe to the first 10 or 100 records, you can also do a limit. It's very important to realize this order that the higher up you are in this order of execution, the more important it is for you to narrow down your search so that your query runs efficiently and on time. Cool. Let's look at the exercise real quick. It's the very end. Okay, let's zoom in a little bit. So we're just importing some variables just to check our code here. That's a Kaggle feature. And we're going to we'll look at this Stack Overflow data set, and let's look a little bit about, let's take a deeper dive in this data set and see how it looks like. This is again a public data set from Bigquery. The data set name is Stack Overflow, and we'll look at the table called post questions. And we're going to look at a few records and see how it looks like. It's very important. So we have an ID, we have a title, we have a body, accepted answer ID, answer count, comment count, creation date, that's useful for analysis. Owner user ID looks like it will also be interesting and useful. Tags, view count, and so forth. Okay, so now that we know a little bit about the data, so that was the post questions. Let's look at the post answers table. See how that looks like. Again, there's an ID for each answer. There's a body, which it looks like an answer to a question above. Comment count, creation date, useful for us for doing time filters. Edit, I don't think we're going to use that a lot. Owner user ID is whoever posed that answer. And parent ID is probably the ID of the question. So in Stack Overflow, if you remember, there's a question at the beginning and there's multiple answers and comments underneath it. So this is just the answers part. Cool, so we're going to look at both tables together. And first thing we're going to look at is how long does it take for questions to receive answers. So I want to take a deeper dive here, and we want to write a query that returns 2 columns. One is the ID of the question, and the other one is time to answer, which is how long it took in seconds for a question to receive an answer. Okay, so let's see how we do that. So we know for sure we're going to need 2 tables, right? So let's take a deeper dive here. So we know we're going to need the questions and the answers table. Now, based on this question here, we don't have a reason to think of providing only questions that did not have answers, or it doesn't make sense to have answers that didn't have a question. So we need both, basically, questions that had answers, since we're looking for time that it took for the question to receive an answer. So basically, that means we need an inner join between these 2 tables. And what is common between them is the question ID and the answer parent ID. If you look at this, answer parent ID here, are basically the same field. So, or that's how they're related. So that's how we're inner joining the questions and the answers. We want to narrow down this to only questions that were posed after. So we're interested in the entire month of January 2018. So that means, from January 1st, right before February 1st. Okay, so now what we need the ID of the question. Okay, we get that from the select statement. Now, how do we figure out the time to answer? How long it took for a question to get an answer? So we have both the question and answer tables. We have both the fields, and each one of them has, if you remember, a creation date. So we have a creation date for the answer. We have a creation date for the question. In SQL, you can do this timestamp diff, and you can also specify the unit metric. In this case, we're looking at this in seconds. So what is the difference between the question and the answer in seconds? And let's say a user answered multiple times to the same question. We only want the first time. Basically, what is the minimum time that that a question got an answer, or a question actually could have multiple answers. We're only interested in this case in the very first time that somebody posed an answer. So we need this min operation here, which is looking at these timestamp differences. So that min operation will be running over different question, that's why we're grouping by question ID. And this timestamp difference, we're going to name it time to answer. We're going to order by it. And let's look how that looks like. Yeah, let me run it. I didn't run it. We're also going to post how many questions were answered, as well as number of questions. So first of all, we look at the this data frame that is returned. We look at the time to answer. We want to make sure that there's nothing, all of them have been answered or not compared to the overall data set. Basically, we're looking for percentage of answered questions. Not all questions are answered. So, and we look at this and it says 100%. So that's a bit weird. I mean, you know that not every question has an answer online on Stack Overflow, as well as the number of questions is about 134K for January 2018. So that's the next point here. It's a bit suspicious. This exercise is saying, that usually on average, 80% of the questions receive an answer. And the total number is about 150 in reality versus 134. So let's see what we did wrong here and how can we correct that. If anybody has any idea, let me know. But basically, we're looking for this percentage of answered questions. It's 100%. It should be less than 100%. So the thing to pay attention here is this join type that we did. We did an inner join. So basically, we look for questions that had answers. So we narrowed our search to a very specific data set. And let's look at the right query we should have done. We should have done a left join. So left join means give me all the questions regardless if there was an answer or not. So nothing else was changed in this query. Let's run it again. Okay, so that's 82%. And there's 162K questions. So now we know that we're looking at the right data set. So the join type was misleading before. We were looking at questions that specifically had answers. Now we're looking at questions. And if you look at the very few last elements, you can see that some questions never got an answer in January. Okay. Any question about this? This was an interesting topic. Let me know. Let me know if there's anything on the chat. Robert, I'm not monitoring the chat.
There's been a lot of chat, but I don't think there are any outstanding questions aside from whether there's been a discussion about what are the differences between the Bigquery SQL version of SQL and some other versions such as Microsoft T-SQL. Do you know anything about that?
Not in detail. I think all of them though are support what is the terminology? Core SQL syntax. They might have additional features that one version has, but not the other one. I know the Microsoft
ANSI standard is the.
Yeah. So I would like to think they both support that, but they might have additional features that that is unique to them.
Right.
Okay. Yeah, if anybody knows, let me know. And I haven't compared them in detail, so I don't know what. I'm sure there are features that one has, but not the other. I just don't know what those features are. All right, let's move on a little bit. Let's say now we're interested in figuring out a little bit from a user perspective. So we're looking at how long does, not how long, but when is the first time that a user is asking a question, or is the first time that a user contributed to an answer based on user ID. So are usually people asking questions, or are they usually providing answers? That'd be an interesting analysis. So the query that we need is, we need to figure out by user ID, the first time that a user asked a question, as well as the first time that a user contributed to an answer. That's what we're looking for right now. And we also want to keep track here of users who have asked questions but have not provided answers. We also want to keep track of users who have answered questions but have not posed their own questions. So that should tell us a little bit about the join type that we should do. And again, to avoid returning too much data, we're only going to look at January 2019. Okay, so let's start with the from statement. We know we need the questions and the answers. Let's name them Q and A. From this statement here, that we want to keep a user regardless if they posed a question or if they answered. So we want to keep an ID or an entry if a user asked a question or if she or he provided an answer. That's why we're doing a full join here. And what is common about them is this owner user ID, both in the question and in the answer tables. Then we want to look at, okay, let's filter a little bit before we look at the different fields. So we're going to look at creation date being January 2019 for questions, as well as January 2019 for answers. We want to look at user ID. We want to group by user ID. And the thing that says here is the first time user asks a question. That usually means some kind of mean operation over some kind of a timestamp. So we have a creation date for questions. We're doing a mean operation here. We're naming that first question. We're also applying this mean operation on the creation date of answers as first answer, and we're grouping by user ID. We can also optionally sort by user ID, which we're doing here. Okay, so now we have sorted by user ID, the first question timestamp and the first answer timestamp. And then there's no specific order. The user, again, could have probably answered first or could have probably raised a question first. Okay, next one. This is, again, this hypothetical example of owners, pets, and treats. And we wanted to do multiple joins. That was the key here. So we wanted to get all the owners and their pets and their treats in one result. And we do that using, so we want a full join of pets and owners. And then for that result, we only want the treats that this owner and pet combination is returning. So there's a full join followed by a left join. And reading online, let's see if I have a link here somewhere. By reading online, the order, if I understood it correctly, is first the full join is done, and then the left join. So it's executed from left to right. Okay, so let's go back to our Stack Overflow dataset. We're interested in understanding users who joined the site in 2019. And we want to basically track a little bit their experience and their journey on Stack Overflow. So we want to see for each user that they joined in Jan 2019, the first time that the user posed a question, as well as the first time that the user provided an answer. This looks like a typo here. So again, this is the order of operation that we saw above from where group by. And multiple joins as well. I have another link here on this notebook. Find it interesting of only do multiple joins on the order of it. Okay, so we also have a new table. Let me see here. We also need a new table called users that contains information when a user joins the website, joins Stack Overflow. That's useful for us. And it has an ID and as well as a creation date when a user joined. Okay, so let's look how we're going to deal with that. The way that I started was I did a common table expression just to get only the relevant users that I want that joined in 2019. I don't want to look at all the users, so I want to limit my search in 2019, January 2019. And I'm just getting the user ID as well as the creation date, which is basically the exact date in Jan 2019 that the user created an account. So I'll store that intermediate result in this intermediate table called users. Then what I will do is I'll look at the questions and I'll look at that users table. And what I did here was a left join of questions with users. So I only got users that questions that were posed by a user that joined in 2019. After that, I did a full join with the answers because I think we need, so there's a statement here that said that, let me go back. questions and answers posed after Jan 2019 should still be included. So the time limit is basically when a user joins, but you can join in Jan, but you can basically ask a question in Feb or reply in March, and we need that, those rows as well. So that was my rationale for doing a full join with the answers, and then we're grouping by user ID and user creation date and ordering by user creation date. Let's run this. So we have a user ID, user creation date, first question, first answer. This is coming from the select here. User ID, user creation date, again, a minimum creation date from the question, a minimum creation date from the answer. I wanted to look at performance a little bit, and actually I wanted to look at what is the right answer for this. So this query is actually wrong. It's returning 142 rows instead of 136 rows. And I don't know if, take a second here, but what could be the reason? And I'm looking at some sample examples here as well. Let me run it.
Hey, George, I don't think you want a full join in there.
Okay, the reason being?
So full join is when you have no matching on the left table and a value in the right table. I don't think that's ever going to happen. Well, I mean, you only want answers that actually belong to questions. So if you want questions that only questions that have answers, you can do an inner join. If you do a left join, you'll get every answer to every question, but you'll still get every question even if it doesn't have any answers.
Mm-hmm.
There's no reason to extend the left join to a full join, I don't think.
Yep. So that's one reason for it. The join needs to be corrected. There's something else as well. I think I corrected later, but there's something else as well that was not giving me the right answer. And let's see. So I was drawn by something specific that said here, let's see, that users need to be joined from or have created an account from Jan 1st to January 31st inclusive. So that made me write this specific query in this specific format of user creation date greater or equal, user creation date less or equal. Now remember, these are timestamps. So this statement is different than me saying less than the next day, which is Feb 1st. So that was another interesting thing here. So one error is this, and the other one is the full join, like you mentioned, Ted. So let's see, once I correct both, what do I get?
So your original query was eliminating everything from January 31st because that timestamp was set to midnight or 0 hours?
Yeah, so I am curious to, I don't know. I think it only peaks maybe the 0th hour. Yeah, I don't know if it peaks every other hour of Jan 31st. I experimented with different join types here. I did a full join of questions and answers and a right join on users. That didn't give me the right number of rows either. It gave me slightly different. Then I corrected here the date, but the full join is still there. So that's again an issue. Then let's see what I did here. Another join. Let's see here. Different order of operations here, but still left full is there. Left full. Okay. I'm still doing, here I'm doing a left and left, which is the right one. I'm not using a common table expression. I'm just filtering for creation dates here. And I'm using this less than. So this is giving me the right one. Another way that I did it was, let me remember. So yeah, so I also did a full, but I put a filter somewhere on user ID. Let me see, where did I do that? I thought there was one where user ID was not null. Okay, so basically the order of operation, right? We need to do a left between user and answer, as well as left between question and user. And again, this creation date was less than the next day, since this is timestamp. So that gave me the right answer. Okay, let's look at the last one for this module. We wanted to see how many distinct users posted on Jan 1st, 2019. So we need a field called owner user ID, that the ID of all users who posted at least one question on answer on Jan 1st. So, or this should tell us a little bit about what kind of operation we should use between the two tables. So we need to combine basically things, and also we need to probably keep unique identifiers. So this looks like a union operation. We have IDs in the question table, we have IDs in the answer table, and yep, each user ID should appear at most once. So this is a union distinct case. So we write the query separately. We figure out what is from the questions, what is the user ID. In this case, I'm extracting the date and setting it equal to Jan 1st. I'm doing the same for answers, Jan 1st, their own user ID, and then just doing a union distinct. And since they're probably integers or strings, and we can do this. And let's run this. So that's a collection of all users that either posed a question or raised an answer or replied with an answer in that specific day. Cool. That was interesting, interesting set of questions. If there are no feedback or questions, let me move into the next module. So we covered union joins. Let's go to analytic functions. I'm going to speed up a little bit here. This is a very interesting feature of SQL. So we've seen aggregate functions in the past. We've seen average, we've seen sum, we've seen count, we've seen min, we've seen max. And those are specific functions that take as input multiple entries and return only one output. But what if we wanted to do something specific for each row in a group? So this is similar to the group by statement that we do in pandas. Let's say we want to do something very specific for each row instead of just returning one result. And we're going to start with this table here. There are two, this is, let's call it like a running or a training table. There are two runners identified by an ID, ID1 and ID2. Each one of them is recording on different days how much they ran that day in minutes, or how much they trained, how long. And you can see here, user 1 on that day trained for 22 minutes, user 2 on that day trained for 28 minutes. Let's say we wanted to figure out what is called a moving average of the training times for each runner. So we want to look at, so this was a little bit ambiguous for me, this statement, where we always take the average of the current and previous training sessions. So if we look at, for example, user 1 here, and if we order this by date, does that mean that we need to take the average of all his previous training sessions, or just the current and the previous? To me, that wasn't super clear from here. Let's say we only want to take the average of the current and the previous training session. Okay, how we do that? We start from the from statement. We look in this train time table. We will select all the fields as well as an additional new field called average time. And that is calculated using this analytic function average over the field time, over some interesting new fields here that we're going to take a look at. So first of all, we want to give results back by ID. We want to do this operation separately for different users, for different IDs. So we're going to partition by ID. Next, we want to order by date. That's important for us because that's how we're going to take the current and the previous training session records. And we want to look at the current row and one preceding the current row. And there's a nice visualization here that explains it better. So this is on the left, the original data set. Again, user IDs are, these are color coded, user ID 1 and 2. We're partitioning by ID. So we have the orange and the green ones here by ID. We're ordering by date, Jan, April, July, so forth. And then what we're doing here is we are introducing a new field, average time, where for the first record, we're taking the average of the current row and the preceding row. We don't have a preceding row, so it's just that value. For the second record, we're taking the average of the current row, which is 26, and the previous one, which is 30. That average is 28. For the third one, we're taking the average of 22, and the previous one, which is 26, and the average is 24. So this is a moving average of the current and the preceding row. And this is exactly what this statement says, rows between one preceding and current row. There are many other things we could have done with this, what are called window frame clauses. We could have done, so we did one preceding and current. We could have done 3 preceding and 1 following if you wanted to look at 3 previous rows, the current row, and the following row, so 4 rows in total. Or we could have done an unbounded moving average on the left and on the right. So for example, we could have done unbounded preceding and unbounded following. So if you remember the mean and average and sum, those are, when we look at a field, those remind me or are very similar to this unbounded case where you look at all the fields, where you look at all the records in a specific field. You don't look at 5 or 10 preceding or following. Cool. This visualization is very important, so I want to make sure everyone gets it. Robert, let me know if there's any question about this specifically. Okay, then we'll look at different types of analytic functions. We looked at average, which falls under the umbrella of analytic aggregate functions. We could have used min or max to return the minimum or maximum of a group of values, the average or the sum, or the count. We would have done something called a navigation function. We could have returned maybe the first value out of a group or the last value. We could have returned the value of preceding or subsequent rows. And we're going to look at some example of those because there are in an SQL statement you can use either of those if the setup is right, and we're going to look at some examples. Another thing we could have done is we could have assigned integer numbers. So we could have done, for example, what is the order in which a row appears in the input, starting with 1. That's the row number feature here. We could have done a rank, which looks at the order, but gives a number that basically what is called ranking. And this explanation might not be the best, but we're going to look at an example based on what that means. Okay, let's look at this San Francisco Open data set. This is a bike share trip table from Bigquery dataset, and let's see how that looks like. So I have a trip ID. Let's look at the code real quick. That's public data, San Francisco, bike share trips. Let's look at the structure of the data. We have a trip ID, we have a duration in seconds, how long the trip took, the start date, the start station name, and the station ID. End date, end station name, and station ID. What is the bike number? Each bike has a unique identifier, zip code, and what kind of subscriber this is. Okay, so let's see what kind of questions we can raise here. So each row of the table corresponds to a different bike trip. And let's say we want cumulative number of trips for each date in 2015. So starting, for example, from January 1st, 2015, how many bike trips we had that day. We're going to add that up to the next day, January 2nd. We're going to add that up to January 3rd, all the way to December 31st. So we want a cumulative number of trips. Okay, so the way we tackle this is, first of all, we want to filter just for 2015. So we start with this table. We only have one table. We'll extract the year equal 2015. Then we want to group by trip date. I want to select the date part of the trip date. And for each trip date, we want to count how many trips were done in that date. So maybe January had 100 trips, January 1st, January 2nd, maybe had 120, and so forth. Okay, now we want to actually sum them up. We want this cumulative number of trips. So we're going to do, on top of the additional fields that we have here, a new field called cumulative trips. We will look at, we will order the previous example, the previous data by trip date. And we will look at rows between unbounded preceding, meaning look all the way from the beginning of Jan 1st, 2015 and current row, and just give us the sum of total bike trips. So let's say if we're in July, that means that sum up all the bike trips from January till July. We run it and let's take a look. So January 1st had 181 trips. Cumulative, that's 181. The next day we had an additional 428. So if we add them up, that's 608. The next day we had 283 if we add them up, and so forth. And so this is basically the cumulative number of trips. And this is just an explanation of why we use the common expression, common table expression, and again, we wanted the current as well as all preceding bike trips. Okay, next one, I think it was an interesting one, if I remember. So this one tracks where each bike began and ended in October 25th on a specific day. Let's look at the result. I think I found that interesting. So we're sorting things now by bike number. This trip time is just the time portion of when the trip happened, ignoring the date. And the first station is, so there's a first station, a last station, there's a start station, and end station. So let's see what those are. So we're looking at the same table again, trips. We're looking at, so start station and end station are going to be the first time that a bike ever started a trip. What is the station ID for that? And we're going to look at the entire unbounded data set. Then we also want to look at what is the final destination for this bike. That's called last station ID. So we have our first, so we have our, call that first station, last station. This start and end, I don't think it's really needed here. And I have another notebook that I worked with. Let me see if I have it open somewhere. Yeah. Let me open it real quick. Analytic functions. Yep. So I was tracking a specific bike. I wanted to see what data is returned and why is it returned that way. So I was looking at this data frame here, which is the one that from the previous example. I was looking at bike number 25 or ID 25. And if you notice, each row is a trip, is a different trip. So it started from 77, it went to station ID 60. This could be, let's say, a metro ID. Then another trip went from 60 to 51. And the first and the last will be basically the first metro ID that this bike went to, and what is the last one, 51. But if I really only care about the first and the last, I don't need a record for each trip, right? I don't need to know what are the intermediate station IDs. So the way, let's see how I did that here. I think I did. Yeah, a group by. So I think I did a group by bike number, and I eliminated the intermediate IDs. So I really didn't care about the intermediate ones. I just wanted for each bike for that specific day. It's a specific day only. When was the metro ID that it started, and when was the last one that it ended? It could have ended. It could have been so many intermediate station IDs. I only want the first and the last. So that was the different query that I did here. I did a group by bike number, and I think that's it. Everything else remained the same. The first and last value were used there to pick the first and last metro ID. So now if I look at 25, I only get one record instead of individual records for each trip ID. Okay. Let's look at the exercise real quick. Let me zoom in a little bit. So we're going to look at the Chicago taxi trips. Let's look at a few records from this public data taxi trips table. And a few things that I noticed with this data set. Let it run. Okay. So each record has a unique key. Each trip has or each driver has a taxi ID. There's a taxi start timestamp, end timestamp, similar to the bike trip that we saw before. How long did the trip last? How long in terms of time? How long was the distance traveled? Some other information about census tract, drop-off area, extras, what was the cost of the trip, payment type, some location if it was available, like latitude, longitude for pickup and drop off, and what was the company that the driver belongs to. So that's the data, and let's see, something that I noticed is I would hope that the start time minus end, or end time minus start time should be the trip seconds, right? But if you look at these few records, they look the same to me. And I don't know why the trip seconds says 60 there, but the start time and end time are the same. Similar for this one is 0, that looks correct. And I don't know why you have so many records with 0. I don't know why that is. Maybe a canceled trip, I'm not sure. Okay, so let's look at maybe the first 1,000 records. So now the data is in a data frame, I can do things like, okay, give me from the first 10,000 records, just the trips where that lasted more than a minute, just so that I want to make sure that this is valid. So this is one of them. Again, the timestamp don't really justify that, but I guess I'll trust this trip seconds. Another one is this looks more reliable. I didn't do the math to figure out if that's truly that many seconds. It looks like no, because this is an hour and 15 minutes probably. Yep. Another one, another one. I wanted to see if some entries had pickup location, latitude, longitude, and some of them did. And I wanted to see if they had drop-off location, and the first 10K records didn't have any. And I also wanted to look at all the different columns. So there's a fare, tips, tolls, extras, trip total, and which is the amount paid, payment type, and so forth. Okay, so first question is, can we predict demand for rides? And the question is, for each day or for each date from January 1st to December 2017, can we get an average number of daily trips? So how are we going to calculate this average? We need a window including the value of the current date along with the values for the preceding 15 days and the following 15 days. So this is not like a typical like 7-day moving average when you only look at the current row and the previous maybe 6 rows. You actually look at the current row, 15 days in the past and 15 days following. You average them out, and that's our average num trips. So this should tell us a little bit that we should need to use some kind of, preceding and following analytic functions or clauses. The way to do this is usually with a city, just to filter for the data that we need in terms of timestamps. So we start with the taxi trip, is only one table. Only look at trips that are between January 1st, 2016 and December 31st. Again, I did the next day just to avoid timestamp issues. We're grouping by trip date. So for each day, return to us how many trips were done each day. So that's our base data set. Then over this base data set, we want to average 15 records before the current record and the 15 records after that. That means we need an average operation or analytic function over what? We need to order by trip date. That's very important. Then we need the rows between 15 preceding and 15 following. So that's really it. And let's see how that looks like. So for each day, again, the select is trip date and the average number of trips. So there's only 2 fields. What is the average number of trips? And if I wanted to plot this, let me set the index to trip date and see how that looks like. So you can see here from 2016 all the way to 2018. So it has like a downtrending trend. Okay, next one is, can we separate them by community area? I won't go much in detail here, but that basically, there's a clue for us to use partition by community area. And let me run this real quick. And this is where we use this rank operation as well, where there was a specific requirement. So for example, for community area, we wanted to rank or give an ID of 1 to the first trip, ID of 2 to the second trip, and so forth. So for each area, we have a start and an end, and we wanted to rank them. And this rank function, let me find an example here. Run this. Yep, so community area 38. Let me look at maybe some other ones, maybe 100. I was looking for some that actually the community area changed. Looks like it's the same. Okay. How much time, next question is how much time elapses between trips? So we have here an example of taxi ID, start time and end time, and we need a new field called previous break, which tells us how many minutes did a taxi driver take, how many minutes of a break did a driver take before the next trip. That'd be a nice feature. So you're getting on a taxi, right, and it's late in the evening. You want to know if your driver took a break before your trip or he's actually back to back. That'd be interesting calculation to do. So we need to calculate this new field, previous break, and the way that we're thinking about it is basically we have to look at the current start or the current start timestamp for our trip. We need to compare that how much time has elapsed from the previous trip end timestamp. So we need some kind of a time difference function here, as well as we need to refer to the current row as well as the previous row. And again, for the first row, there's no previous trip, so we're going to get another number in that. Okay, so let's see how we do that. We're going to look at the trips. We're going to filter for specific date just to keep the data under control. We'll look at the start time and end time, and actually we want a new field, the break field, which is the time difference between the current trip start time and the last value of an analytic function here, which is the last value of the previous trip. And the way to calculate that is look at the last value of end timestamp. We partition by taxi ID. We want this for each different driver, and we order them by start time. So let's see how that looks like. So maybe the order of time diff is important here, or maybe I'm doing something wrong. Let's see. So I'm getting for each taxi ID here, we're getting a start time of 8, 9. I'm getting -60, which should be +60. I'm doing probably a start minus end. Let's see. Yep, so I'm doing a start minus end. I should have done probably an end minus start. That's one. I also wanted to see a specific driver to see how these values look like. So I'm looking at a specific one here. And another way to do this is instead of last value, you can also use this lag function 1 to also give you the same result. Let's run it. So this doesn't look like it's ordered. That's why we get a bunch of NAs. Last value and lag. And I want to look at difference of them. Something doesn't look right. Let me see. Maybe the order. So let's look at this one, for example. So the previous trip ended at 10:15. The next one started at 11. So that's 45. That's correct. The next one ended at 11. The next one started at 12. That's a 6-minute break. That's correct. I'm not sure where this record came from because there's a record that ended at 12:30, but it started at 12. So that's -30. So I'm a little bit skeptical about this record. Also, as well as this record where it ended at 12. Yeah, these two records are a little bit skeptical for me. I'm not sure.
Hey, George.
Yeah.
In your order by, you ordered by start date, but there's multiple rows with the same start time, and that's causing some confusion. If you change your order by to be start time, comma, end time, then you'll still get weird things because you have these canceled trips, but your results will look more normal to the eye when you inspect them.
Okay, so let's see. Oh, I don't have an order here. I just have a.
Right, but in your partition, in your over clause, if you also order by start and end, that will help, because right now you're getting different. It's sequencing the rows in a different order when you have ties, then it's displaying them at the end when you have ties, and so that's why it looks weird to you. But if you do that, it'll always look at them in the same order that.
Okay,
and then
so
if you also put that.
Got it.
Yeah.
Order by start and end time.
Yeah, and then if you put the same order by in your overall query, then the partition will always be looking in the same sequence as it's printing out the results at the end.
Do another order by here at the very end, you're saying?
or else you could, you could sort it when you're just
Oh.
picking that one driver.
Yeah, in the data frame, right? Yeah.
But either way, just so that you're seeing the exact same order.
Yeah, let's take a look. No, I lost the driver. Maybe I need the driver ID as well. Okay. So first one is looks like he only has one record. Then the second one, there's a trip 10 to 10:45. That's the first record for this taxi ID. Then 30 minutes later, then no break here, 4:15, 0 break, 6:15, 19, 165 minutes. Okay, this makes more sense. It's easier to understand and easier to read, I guess. Yeah, thank you, Dad. Cool. All right. This was the exercise. Any questions in the comments? I haven't checked. Let me know, Robert. Okay. Then the next one, we will be talking a little bit about nested and repeated data, and some nice features that SQL and also Bigquery offers for us. So let's say in this hypothetical example, we have a pet table and a toy table, and we have a pet ID as well. And maybe, so one way to group this is in separate tables as pets and toys. Another one is to actually aggregate these two tables into what, or actually consolidate them into one table. That we would have a pets and toys table like over here. So we have a name, an age, an animal, and a toy. Each toy has its own name as well as its own type. So it could be, frisbee or feather or castle, and as well as the name of the toy, Eddie in this case. So the way we do that when we define our schema, when we create this data set is now the type of the field toy won't be a string, won't be an ID, won't be integer, won't be date. It will be actually a record. So that means it's a collection of something. It's what is called, it's a nested column. So that record of type is comprised of two subtypes, a name and a type, and both of them are string fields. And to query them, we need to refer to the parent name or the parent field name here, toy, dot something. That something is the nested field. So it could be a name or it could be a type. So for example, if we wanted all the pets that have a toy on, as well as the toy name and the toy type, we would select so from the pets and toys, this combined table, we would select the pet name, the toy name, as toy.name because this is a nested field, remember, as well as the toy.type as toy type, and we'll get this table. Other than that, everything else remains the same. It's just that the reference is different now for nested types. Okay, let's look at repeated data. Let's say that an animal could have multiple toys. So if we represent this in regular, database design, could have done this with separate tables like this, pets and toys type. So that means that pet ID 1, which is Napoleon here. No, that's Moon. Has a frisbee, a bone, and a rope. And that's easier to understand if we look at this combined table here, pets and toys type, where it's very easy to see that the dog Moon has 3 toys, frisbee, bone, and rope. The next one has 2, cat, the fish only has a castle. And we look at the schema of this new table here, we see that the toys field and column is actually of repeated, has this repeated mode. That means that it's basically an array, like from a Python or JavaScript world. Okay, then when we query this, how do we actually get the data out of it? We have to use this operator called unnest. So we look at the pet names and the toy type, but now the toy type, we need to unnest the toys field right here. That means give me a record for each unique combination of toys. So this will return us Moon Frisbee, Moon Bone, Moon Rope, because Moon has 3 toys, the next one has 2 toys, and the last fish has only 1 castle. And this is just another visualization of how the unnesting works. Okay, we could have nested and repeated data. So let's say we have pets, we have a lot of toys who have a lot of names. And let's look at this example, for example, the very first record. So the dog Moon has multiple toys, and each one of them has a name and a type. So it's both repeated because it's a list. Yeah, it has multiple records, but it also nested because there's a structure for each record. It has a name and a type. So this one, if we look at the schema, there's a record and repeated mode or record. And how do we read this data? So first of all, we need to unnest the, so this is a list, right? So we need to unnest the toys column as T. Now within T, we actually get, we need to also step 1 level down into getting the name and the type. And that's how we get the combined data. Okay, let's look at a more realistic example which combines, both repeated and nested data. We're going to look at a Google Analytics sample, and let's look at this data set real quick. So these are coming from Google's e-commerce website, and some questions can be asked. Now, there's a lot of questions here, but we're going to look at some of them. Which website or which part of the domain are users visiting the most? Let's see, maybe what browser they're using or what device they're using and so forth. So we're going to look at the public data again. Google Analytics example is the sample is the data set, and the table we're going to look at is only one specific day. So it's 2017, August 1st. There's so much data in it. We look at a very first few records. There's a visitor ID, right? It looks like empty. Visitor number, visit ID, visit start time, date, and then totals looks like a nested field. You see it has visit, hits, page views, and so forth. Traffic source, device, GeoNetwork, custom dimensions. This looks like a list. Hits looks like a list again. Repeat it. Full visitor ID, channel, and so forth. So we can't really see all the content. So let's take a deeper dive here. And there's a data dictionary if if you're interested in what do all these fields mean. So you can see here user ID, overridden user ID, sent to analytics, visit ID, and identifier for the session. Totals is a record. So it's a nested field, has subfields like bounces, hits, new visits, page views, screen views, and so forth. Okay, let's say we're interested in totals and device. We want to pull out some information from the totals field, which is of type record, as well as the device, which is of type record. And let's say we want the browser field from the device, as well as the transaction field from the totals column. So these are nested. So how are we going to do that? We'll look at our table. We want to pull the browser from device as device browser. We want to pull transactions field from totals. In this case, we're actually doing a sum over all the transactions we're grouping them by device, browser, and how many transactions we have. And we're ordering them by transaction, so we can see how many transactions happened by each browser. I remember the browser was a subfield. Let's find it here. Let's search for it actually. Yep, so under device, it was the very first field. And transactions is right here under totals. That's why we did totals transactions or total.browser as well here to unnest it or to access it, sorry. Okay, something else we want to look at, the heads column. We want to look maybe at head number, page path, and so forth. So the heads, it's a list actually, and we need to unnest it first here. We want to look at, for each heads has this subfields page, which also has a subfield page path. And we want to take account of that. And we want to make sure that it was visited. So head number should be 1. We want to group it by path and order it by count. So basically we want to have an idea of which subdomains or which part of our e-commerce website are visited the most. And you can see here, people are visiting home, and the last one is the basket. Okay, let's look at the example real quick. We will look at the GitHub repo dataset. This is another publicly available dataset on Bigquery. And let's open it a little bit. This one has a lot of data. So if you remember from our previous session, we have to be a little bit careful how much data we read because we have a limit on 5 terabyte of data scan with Bigquery. So we have to be careful with that. So as you can see here, there's a commit ID, a tree where the commit belongs to parent, author, committer, subject, message, and a few other fields. So let's see what we're interested in looking at. So we want to look at maybe by a repository and figure out which repository had most commits in a specific year. Or not which repository, but maybe which individual user made most commits in specific year. So we're going to look at the public data again. We're going to look at GitHub repository dataset. There's a smaller table. We're not going to look at the entire table. There's a smaller table called sample commits that we're going to focus on. Again, the structure is commit, tree, parent, author. See, this looks like a nested field. Committer, nested. Subject, message, trailer. This looks like a list. Difference, repo name, and coding. So let's look at the schema to get an idea of how it looks like. So regular field, author is a record, so it's nested. Committer is also a record, and along with a few other fields. So we want to we're interested in a query that gives us the individuals with most commits in this table. So basically we need 2 fields, a committer name. So there's a committer field here. We're interested in this part here, name, as well as number of commits. And we want to sort it by that number of commits. So we want to figure out who is the busiest committer. Okay, so we're going to do that. Let's look at this table, sample commits. If we remember, committer had a field name called name, so committer.name, we need that. We also need to count how many commits are done by each committer name. That's why we're doing this group by and count. And we're just ordering by number of commits here. So let's run this. So now we sorted by user and by commits. Looks like Linus is here as well, the inventor of Linux. It's very busy. So that's the order. Let's look at another question. Let's look maybe at another table called languages. Let's see how that looks like. Has only 2 fields, has a repository name and a list of all the languages that a repository uses. So if you remember from GitHub, when you log in, when you access a repository, it tells you it's 50% JavaScript, 20%, Python, 1% SQL, or maybe not SQL, but Bash or some other programming languages. And this is a list of what is repository comprised of. Let's see what kind of questions we can answer. There's also a bytes field which tells you this many bytes are written in this language. Okay, let's look at the schema. So we have a repo name and we have a language which is repeated and record type. So the language has its own name as well as bytes. That means that it contains a list of these collections of language name and bytes written there. Here's one very simple example. Let's say we have repo 1, repo 2, repo 3. Repo 1 it has 600 bytes written in language C, 300 bytes written in C++, and 100 bytes written in Shell. Repo 2 is made of Python HTML, and repo 3 is made in Java. If we want to look at all these records, language, remember, is a nested, or is of a record type. Actually, it's repeated, so we need to unnest it. That's what we're doing here with unnest language. And the question is, if we do this, how many records we're going to get? And remember, we're going to unnest the language type. So how many languages are there? Basically, unique languages, and there's for each repo. So repo 1 has 3, C++ Shell. Repo 2 has 2. So that's 3 plus 2, 5. And the last one is 1, 6. So that's the answer to this question here. Okay, we want to look at what is the most popular programming language. So we're going to sort, we need 2 fields, language name, as well as number of repositories in the language table that use that programming language. So again, we're going to look at the languages table. We're going to unnest the language one, the language field. We'll look at the name of it. We're going to count how many repositories are using that language. So across basically all repositories, which language is used the most? Oh, looks like I didn't run time. Yep, I was trying to time the query here. Okay, so in this sample here, looks like JavaScript is mentioned in most repositories, then CSS, HTML, Shell, Python, and some other ones at the very bottom. Surprise JSON is only one. Blade, I'm not sure what that is. CodeQL, not sure. Let me remember what I was trying to do here. I think I was just writing this in different ways. So one is like that, group by language number. Another one is city of unnesting the language, and then within that, just doing a count. Okay, that's similar. I want to see how long that took. 2.2 seconds, 1.5, okay, half a second more. I think this is the same. Okay, last question. We actually want to look at that byte field that we had before. So we're going to look at now at the name of the programming language, but we want to maybe order by which language uses most bytes. Is that true? No, that's what I thought, but it looks like we're not doing any sum over bytes here. We're just looking at a specific repository. We're looking at the language name and the bytes, and yeah, we're ordering by byte descending. So let's see. So for this specific repository, basically we just want to order a list of languages used and which one is the most heavily used. So this one is using most bytes, then C, then Mercury, and so forth. Okay, that's what I had for nested and repeated. Let me know if there's any questions. Otherwise, I'll go to the last session for today. Okay, that was GitHub. Okay, the last one is writing efficient queries. Okay, zoom in a little bit. So we've seen different examples. We've seen different joins, unions. We've seen nested types. We've seen analytic functions. And then the question now becomes, okay, you're going to roll this probably in production, or you're going to roll it somewhere to be executed. And the question is, do you run this once a time? Do you run this every week, every day? How much data are you looking at? How important is execution time versus how much data you're scanning on your database? So these are things that you need to consider before you roll this into a complicated query into production. So to measure the performance of some of our queries, we're going to create two functions here. We're going to look at the amount of data that a Bigquery is looking at. Remember, we have a limit on our monthly expenditure of Bigquery of 5 terabytes per month, as well as we're going to look at how long does a query run. So these are just some very basic functions we're going to create. And in Bigquery, we have this nice feature called query job configuration. If we set this parameter called dry run true, it will not actually count towards our usage. So if we run a query, so we have a query as input. If we run it with this job config where dry run is true, it will tell us, if we access total bytes process, it will tell us how much data the query would scan, and that would count towards our usage. Another auxiliary function we're going to use is time to run. So we have this, we're actually going to run the query, and we're just going to count the start and end time. I'm just going to take the difference like I was doing before. Okay, so then this is just to show you the very first strategy. So there are some strategies that can help us with writing efficient queries. One of them is select only the things that you need. So if you remember here in our order, right, we had the from, where, group by, having, select. Typically, I would start with the very first one from, but here we're just talking about order number 5, select. And let's see what difference that makes. So we're looking, for example, at this GitHub repo content field or table. This is a table. We're looking at every field. I have no idea how many fields are there, probably a lot, versus just looking at maybe the size and binary fields and look at the difference. So the first one has almost 2.5 terabytes, 2,500 gigabytes of data scanned, versus the second query only has 2 gigs of data scanned. That's because probably there's a text field here in this content table that has a lot of information. That's, there's 1,000x difference. So definitely know what you're looking for before you do this select star. I guess that applies to import when you import things on Python as well, right? Are you sure you need every module, or just import whatever you need? The other thing is this has to do with join operations. And actually, do you need to, let me see if this is join or, so we're trying to calculate the average duration in one-way bike trips in this bike share trips. And let's see, so we have 2 queries. One of them is looking at station ID, and the other one is looking at station name. And the observation here is that you can use either, like you don't need to use both. So figure out which one uses less data or makes your query a little bit more efficient and stick with that. So for example, what we're doing here is we're looking at station ID for where and group by, but we're selecting station name, and average. So basically we're exposing our query to multiple fields. The other way to do this would be just looking at station name in the where clause and the group by as well as in the select. There's no ID here. And let's look at the difference. It's not a huge difference. First one is 0.076, the other one is 0.06. But again, this is using this one-to-one relationship of station ID and station name. This is not terribly, that's not a huge difference. So maybe you're not going to get a lot of gain here. But I think the query on the second part looks a little bit cleaner than the first one. The other one, the most important one, according to me, is this joins, right? So I want to make sure that you avoid unnecessary joins. So let's say we have a pet table, an owner table. We do a join. This is what is called a one-to-one join, because one pet has one owner and one owner has one pet. But what if an owner or what if a pet belongs to multiple owners? Let's say an n-to-one join. So in this case, the Ripley here, the cat, belongs to both Chet and Avet. So that's an n-to-one join. So basically we need to figure out for each owner, what is their pet? And again, an owner or a pet can belong to multiple owners. We could have also something in the opposite direction. We can have, let's look at the result. We can have two people owning multiple pets, or multiple people owning multiple pets. That's an end-to-end join, basically. So for example, Chet and Avet have a cat, Ripley, as well as a spider named Brian, as well as a mouse, Baby. So they're pretty busy, basically. And Jules only has a dog, and Aubrey only has a rabbit. Okay, so let's look now at our GitHub repository data set. And we want to count number of distinct committers and number of files in a very specific subset of repositories. So that's the key here. We're only looking at very specific subset. So the long way to do this would be to get the commits table and get the files table, inner join them on repo name, and then do the where statement. And if you remember here, it's already late, too late for us because we're doing a huge join here and then we're filtering down. Okay, let's see how long that takes. That takes about 1200 seconds. Let's see how we can make this easier, right? So easier meaning look only at subset of data. So we use CTEs, common table expression. So we look at only the committers and only the repositories from each setting. We don't want to join on every repository. We want to look at the specific subset. If there's any field that needs to be unnested, we do that as well. Another CTE here, comma. This is second CTE, the files. We only look at these repositories. And then we finally inner join them right here on repository name. That gives us an execution time of 4 seconds. So that's a huge difference. All right, we didn't have to join repository, and we didn't have to join committers and files for every repository. We're only interested in this 7 repositories here. Cool. So there are some more strategies that this notebook is directing us on this O'Reilly book on the definite guide. I took a quick look. It says a little bit about what is Bigquery, query essentials, aggregates, data types, operators, loading data. We haven't tried that yet. Developing, we did this a little bit. We've seen Bigquery used, from Python. We also have seen it from the console of Google Cloud. Architecture, this is going under the hood and uses this Dremel technology that Google developed many years ago. And then optimizing. This is where we're talking right now. So speed, efficiency of joins, maybe you can cache results. Not sure this approximate aggregation functions. Sounds interesting. And window functions. And also Bigquery has this feature of you can actually develop machine learning, deep learning models as you're pulling data from your backend. So you can do that as well. Then security, zones. So a little bit of everything, I would say. Okay, let's go back here. Let's go to our last exercise. This is not as complicated as the other ones we've seen so far. So we have a scenario here where we're giving 3 scenarios. We're looking at a pet costume company. So they sell pet costumes. And they're giving us 3 queries, and they're basically asking us which one you prioritize in making more efficient. So the first one is the software developer is writing an app that basically tells you, looks at different tables like order table, shipment table, and a warehouse location table. And an employee can pull out the app and it can look for, okay, for this order, I need to go to this warehouse location to fulfill this shipment. So it's basically looking at 3 tables, and that's, you want to look at what items need to be shipped and which aisle of the warehouse to go to get these items. It's like a fulfillment center, basically. Another one is you want to look at the list of all customer reviews and complaints, which are conveniently stored into one single table, reviews table. Some of the reviews can be long, some of your costumes for parrots, maybe all of you can take a look here, but there's some parrot costumes for parrots. People love them. And maybe some of these reviews are long. And the other one is we have owners, dog owners specifically, and you develop this costume with a GPS tracker and a wireless communication device. And that is basically feeding data into your backend very often. It says here, I think, once a second. Then you want users to log into your website and you want them to search for their costume, hopefully in case they can't find their dog, or they want to see, well, where's the costume, maybe after washing it, I don't know. So you want to basically locate the costume locations. So you have 2 tables. You have a costume locations that has information about where is the costume, what is the exact location, as well as the owner table, which pairs an owner with a costume ID. So the question is, which one do you optimize?
Do Qubit and Butter have costumes?
I'm working on it. Yeah, I'm working on it. I have a lot of requests for them. Apparently, people are eager to see them on hats. I don't know why. Guinea pigs on tiny hats. So I said 3. Let's see. Let me run this actually. So yeah, the third one, you have data being sent every second. So you definitely want to make sure that the queries that you run are the most efficient in terms of data scanned as well as time executed. Maybe the second one you want to optimize is the fulfillment center one. Maybe the last one is the reviews one, which doesn't involve any joins. It's just a large table. Okay, so let's look at another example. This is a costume location table, some samples. We have a costume ID, a timestamp, and a location. Then we have a costume owners, which tells us that owner 490, whoever that is, owns costume ID 1. And that's, here we have records for where the costume geographically is located for different timestamps. Okay, so the scenario is Mitzi the dog recently ran off chasing a squirrel. That's the scenario, but thankfully she was lost seeing in her hot dog costume. Okay, I couldn't find a picture that could describe this, and I think it was a little bit unfair to the squirrel. So all I could find was a picture of a dog with a squirrel costume on top of it. So the owner of Mitzi, let's see, with ID, Mitzi owner ID logs into their website. I want to pull the last location. Currently, we get this information by running the following query, and let's see if we can optimize it a little bit, right? So we have the custom owners. Sorry, I double clicked. So we have the custom owners, which is custom ID and owner ID, and then we have custom locations, timestamp locations. So let's see. So first of all, select star. That doesn't look right. And then also what we're doing, we're inner joining costume owners and custom locations on ID. So basically, we're joining every record for every owner with every location out there, and that's not right. That doesn't look right. This location and owners, we don't need that actually. Then what are we doing here? On that, that's one city. In other cities, we're looking at for each costume ID, we're looking at the most recent timestamp. Okay, do we really need that? And for each costume ID, again, we're just maybe interested in Mitzi owner ID here. Then in the end, what we're doing, we're combining this common table expressions on timestamp as well as costume ID. So is there a way to make this faster or cheaper? Okay, so we have a start here, we have an inner join, no filter or no where. So this definitely is not the right approach. So do you see any merges in the query? Yes. So working with this table locations and owners table is very inefficient because it's a huge table. You don't need all combinations of owners and locations. You don't. You're only looking at a specific user. So one improvement could be, again, the where statement here, as well as the select. You only need the costume ID. So you need the current owner costumes. That's one CTE. So that gives us basically the costume ID. Then another CTE would be looking at the timestamp, the costume ID, and the location. We're interested in what is the timestamp location for that costume ID. And the last one is what is the max timestamp. But the major improvement is right here, right? That's the huge improvement that we did. And let's see the order of joins here. What we're doing, we are looking at owner custom locations, which is this one. Inner join was last seen on timestamp, and so we have owner custom location, which is this one. Inner join with last seen, yep. But owner custom locations is actually inner joined with our current owner. So right now, this is a very small data set right here. So the efficiency that we gained from the first common table expression propagated to the second common expression, where now we're only joining custom IDs and timestamps only for the Mitzi owner ID. So again, instead of doing large merges, we're doing only specific subsets of, we're looking only at a very small data set. And there's a note here that a lot of databases have something called a query planner, which will try to optimize a few things for you, but you shouldn't necessarily rely on them when you do your query. Yep. So yeah, this is just a note that if in the second case, we're probably looking at 99% fewer rows than in the first case, which was this one. Cool. I see a lot of traffic on chat, so I don't know what's the status, but that's all I had for us, friends. I'll pause here. This is a lot of information, and again, play around with the notebooks. Let us know if you have any questions or join us on Slack if you're stuck somewhere, or if you want to share anything useful with us. Some other resources that I found, on lag, or so this is on lag. So if you want to do something, maybe you want to compare the current month with the previous month, you can do maybe a lag by 1. Bigquery has that analytic schema where we saw with the online purchases that you saw, the book, and different data sets on Bigquery. So we've seen a few. We've seen Stack Overflow, GitHub, bike trips, but there's a lot more out there. Maybe we can use some of them for our upcoming coding challenges. Cool. All right, friends, I'll pause here. Thank you for joining us. Let me know if you have any feedback or comments. This was an interesting session. So that concludes our SQL sessions. We have 2 more sessions coming up next week on data cleaning and geospatial analysis. And then after that, we're going to dive more into ML and deep learning. Yes, I can post some of those links. That was for the window functions. That's the book. Yep, you're welcome. Thank you, Sadesh. And in case you're interested in more data sets. Cool. I'll stop sharing. Thank you, friends. I really appreciate it. Let me stop recording here.